Starting in section 4.9 and through the rest of the sections for the remainder of the semester, we're going to talk about antiderivatives, which are going to be derivatives in reverse. So somebody else has already taken the derivative of a function, and our goal is going to be to take that derivative and reverse their process and turn it back into the original function. So think about this for just a second. Say somebody told you that f prime of x equals 2x, and they said f of x is what? So they've already done the derivative of some function, and they want to know what that function is. They want to know who has a derivative of 2x. So you might be able to figure this one out just by remembering some things you did with derivatives. I'm going to teach you some different rules so that this is easier to figure out, but you might be able to just remember off the top of your head that f of x is going to be x squared. If you take the derivative of x squared, you get 2x. But think about this. What is the derivative of x squared plus 5? That's also 2x. What is the derivative of x squared minus 20? That's also 2x. What is the derivative of x squared plus 100? That's also 2x. And I'm doing this for a reason, obviously, because when we do antiderivatives, don't forget, when we take a derivative, our original function could have a constant whose derivative is equal to 0. So when all we're given is the derivative, we won't know if our original function had a constant term or not. So we have to indicate that in our answer. So anytime we do some sort of antiderivative problem, we always say that the antiderivative, first of all, what we're doing is we are reversing the derivative process. And you may be interested to know, back when all of this stuff was first discovered, it was actually antiderivatives that were discovered before derivatives. But they figured out it was actually easier to teach derivatives first than it was to teach antiderivatives. But it was the antiderivative stuff that was discovered first, and the derivatives that were discovered second. So really all we're doing here with antiderivatives is we are reversing the derivative process. And because derivatives of constants are 0, we won't know and we won't see them in the derivative. So when we do the antiderivative and we say our final answer, technically we have to account for that. So we would say f of x is x squared plus possibly some constant. And we call this c here an arbitrary constant. There could be this arbitrary constant. We don't know, but we don't want to just completely leave it out because we don't have enough information to say that it doesn't exist, or if it does exist, we don't know the value of it. And we want to give a full and complete answer for our antiderivative. So anytime you do an antiderivative, we always attach plus c to our answer. So you will see that throughout the next couple of sections. Anytime we do an antiderivative, there's always a plus c, unless for some reason they give us some sort of information that's going to allow us to solve. And then we wouldn't need to do it, but we'll talk about that as it comes up. But we're just reversing this derivative process, and we'll always have this arbitrary constant, which is plus c on our answer, and we call it c just because it's the first letter of constant. It really could be any any letter whatsoever. We just use C for constant. Kind of like when we first learn about functions, we use the letter F, F for function. And we do it for a lot of different things in math. We just use a convenient letter to represent whatever we're talking about. So this is kind of the idea that we're going to use. Somebody has already taken the derivative, and our goal is going to be to undo that derivative. So derivatives and antiderivatives are kind of like opposite operations. Some of them you might just be able to look at and tell what the antiderivative is. Some of them are not going to be that simple, and we really need to learn some sort of process in order to figure out what the antiderivative is. So I'm going to go through some more concrete processes of how to do that. But I wanted to talk about this first. On all of these answers, don't forget your plus C, because MyLabs Plus will mark you wrong if you do not remember to put the plus C on your answer. So the first and easiest one to do is if you remember that derivative equals slope. So if you're told that your derivative is a constant, so for example, f prime is equal to just the number 5. What kind of function has a constant slope? The slope is always the same everywhere on the function. The slope never changes. The slope for this example is always 5. The type of function that has a constant slope is a line. So our original function must be a line with a slope of 5. The only thing we don't know is the intercept for that function, which is the plus C part. We know that's going to be a straight line with a slope of 5. We just don't know the intercept. So the first rule we're going to see here is the constant rule. The antiderivative, and there's a couple of ways we can actually write this more mathematically. You're not always going to see it written as f prime. The antiderivative of any constant, and I don't want to use the letter C because we always use C as our arbitrary constant here at the end, but the antiderivative of any constant K is Kx plus C. Because remember, what we're talking about is undoing a derivative. So some little bit of notation here. A couple of different ways that we could be presented these types of problems, and there's 3 different ways I'm going to write this, and they all mean the exact same thing. We could be given, so I'm going to use an example, and I'm going to say f prime of x equals 3. That means that f of x equals 3x plus c. The next one's going to look kind of weird. If we're told that f of x, so this is number 1. If they say f of x equals 3, and they say find the antiderivative, so they didn't give it in derivative notation. So we can't use f for our answer because they used f in the question. So what we do is we use capital F. Don't get too worried about the notation. Just know that if it says do antiderivative, just worry about getting the function part of the answer correct. they'll always already include that part of the answer already in the problem for you, so you don't really need to worry about that part. But if the original part has f prime, then your answer is going to have f because you're undoing that derivative. If the original problem uses f as the derivative, then the antiderivative is going to be capital F. What you're going to see more and more in the next few sections is a new symbol called the integral symbol, which means take the antiderivative. And the dx means with respect to x. That means use x as your variable in this problem. So that kind of tall, thin S symbol means take the antiderivative. So they're not giving it to us in function notation. They're just saying take the antiderivative of 3 and use x as your variable when you do it. So then all we would say is that this is equal to, we wouldn't even write it in function notation as our answer. We would say this is equal to 3x plus c. So this third option here doesn't use function notation at all. It just says, and if you ignore my arrow, we would say the antiderivative of 3 with respect to x is 3x plus c. So I'm going to try to highlight some of these pieces that match up. The antiderivative, that's this piece, of 3, that's this piece, with respect to x, that's what this piece means. Is equals means is, and then we've got our answer, 3 times x plus some arbitrary constant c. So that's if we just wanted to write the whole thing out like as a question and an answer, just as one kind of smooth equation, rather than just two separate functions. And this notation here in option number 3 is much more common, and it's what we're going to be seeing more and more throughout the rest of these last few sections. And if you plan on taking Calculus 2, this is really the most common notation that you're going to see is this really tall, thin S symbol that we call the integration symbol. And anytime you see that integration symbol, it means take the antiderivative or find the antiderivative. It means somebody else already took the derivative and we want to undo it. Okay? So we've got our constant rule. It is linear functions who have a constant as a derivative. That's our first antiderivative rule. The next, probably easiest rule we used up here in the very first problem, and it's called the power rule. when I asked you what the antiderivative of 2x was. If we said f prime is 2x, the original function must have been x squared. There is a power rule that could be used for that, along with any other function that can be written as a power. And it doesn't just have to be a positive whole number power. It could be a fractional power, which means it's a root, or it could be a negative power, which means it's technically an x in the denominator. So this power rule is really, really important. So the integral of x to the n with respect to x, anytime you're asked to find the antiderivative of x to some power, and n can be anything except for -1. We're going to have a separate rule if n is -1, and I'll show you what happens if n is -1. We'll run into a problem. So it'll be obvious if you try this on n equals -1, it'll be obvious that you can't do it. But as long as n is not -1, remember there is a power rule for derivatives. The power rule for derivatives says you bring your old power out front and then you subtract 1 for your new power. Well, we kind of have to do the opposite. If derivatives and antiderivatives are kind of like opposite operations, we need to do the opposite to figure out the antiderivative. So for the antiderivative, the power is going to go up. So we're going to have x to the n plus 1. Whoever took the derivative made the power go down. We need to make the power go back up. And then with derivatives, we usually multiply by the old exponent. With antiderivatives, we are going to divide, or what I like to do is multiply by the reciprocal of the new exponent. And then we always add that arbitrary constant at the end. If you tried to do this for n equals -1, look what happens. The integral of x to the -1 dx. If we added 1 to that, -1 plus 1 is 0. And then we take that new power and we divide by it in the front. We multiply by 1 over it in the front. You cannot put 0 in the denominator. That fraction is undefined. So nope, we cannot do this. So that is why this rule does not work for n equals -1. We can do it for every other power, including fractions and negatives. We just cannot do it for -1. We're going to have a separate rule for -1. So let's look at some examples where it does work. If we wanted the antiderivative for x to the 5th. So the rule is to, the derivative brought the power down. We want the power to go back up. And then whatever that new power is, we flip it out front for a coefficient. And it's as easy as that. And you can always check to see if this works, because if we were to go back this direction, it would be derivative. So what we just did is antiderivative. And then if we want to check it, we can take the derivative of 1/6 x to the 6th and see if it gives us back x to the 5th. So it's like a little circle. They should just go back and forth to each other if we do derivative and antiderivative. Antiderivative of cubed root of x with respect to x. This one we can also do with power rule, because cubed root of x can be written as a power. We just have to rewrite it first. So cubed root of x is x to the 1/3. And then we can use the power rule we had above. So we said we are going to, derivative makes the power go down 1. So we're going to make the power go back up 1. So 1/3 plus 1 is 4/3. And technically we said we're going to take that power and put it in the denominator in the front. But that is not mathematically legal to leave it like that. Dividing by a fraction is the same as multiplying by the reciprocal. So we would have to fix this. We wouldn't leave it as 1 divided by 4/3. We would go ahead and flip that and say this is 3/4 x to the 4/3 plus c. So it works for radicals as well. It also works for x's in the denominator. So if we had 1 over x cubed. Now, you can't do the power rule the way it's written right now. We would have to bring that x cubed to the numerator using a negative power first. And then once we have it out of the fraction and pulled up to our numerator, then we could use our power rule on it. So remember, the derivative brought the power down, and then for antiderivative, we want to make the power go back up. And by up, I'm meaning add 1. So the rule is to add 1. So -3 plus 1 is -2. And then we take that new power and we flip it out front for a coefficient. And if you want to, you could rewrite this, since our power is still negative. We could rewrite that back in the denominator. Since we have a fraction in front already, we wouldn't have to write 2 separate fractions. We could write the whole thing just in one big fraction as -1 over 2x squared plus c. So it works for just regular powers of x, it works for radicals, and it works for powers that are written in denominators, because we can pull them up to the numerator with negative powers. It works for all of them. So that one case that we had up here with x to the -1, that is a special rule all of its own, and you may remember it. We had a special derivative, and I'm not going to give it away right away, but there was something that we took the derivative of, and when we did, we got 1 over x as the answer. Technically, 1 over x is x to the -1. So this process is derivative. To go from left to right is derivative. What we're trying to do now in 4.9 is take the x to the -1 and go backwards with it and figure out what goes in those brackets. That's the antiderivative. So to say what is the antiderivative of x to the -1 dx means I want to know what you took the derivative of to get 1 over x, or x to the -1. And you can't do the power rule on it. We just showed up here that you get that 1 divided by 0. We're not allowed to divide by 0. So there is a special function whose antiderivative is 1 over x, or x to the -1. And I will finally give it away. It is natural log of x. But there's something special we need to do here. We've got to put absolute values on our x. And the reason is we want to make sure that the domain of this function is the same as the domain for this function. Now, right now, the only thing that x to the -1 can't use is 0. X to the -1, I can plug negatives in there and get answers. I can plug positives in there and get answers. X to the -1 is just not defined at 0. So I want to make sure that I could use all of the same numbers in my answer. Well, when I do my antiderivative, it turns into a log. And the log function is only defined for positive values of x. So that's not good. All of a sudden, I've excluded half of the domain. So in order to fix that, what we do is we put these absolute value bars around our x, which means we can now use the whole negative side as well. Because the absolute value bars, if for some reason we did want to use the negative side, and I plugged a negative value in for the x, the absolute value bars will switch it to a positive so that it can be evaluated inside the log function. So the absolute value bars are so that the domains for x to the negative 1 and the natural log of x match up. Anytime you answer an antiderivative with a natural log, you're going to have absolute values in your answer. You're going to have absolute values around whatever is inside your log. Just to be safe. So that's what we do when we have an x to the negative 1. And for section 4.9, we don't want to forget about all of the trig that we've learned. So first, let me write these as derivatives. We said the derivative for sine of x is cosine of x. The derivative for cosine of x is negative sine of x. The derivative for tangent of x is secant squared of x. The derivative for cosecant x is negative cosecant cotangent. The derivative for for secant is secant x tangent x. And then the derivative for cotangent x is negative cosecant squared x. So those were all of our trig derivatives. Now the only thing different now with antiderivatives is we're going to be starting on the right. That's going to be the question, and then the left is going to be the answer. So we're going to be going this direction for antiderivatives. And usually the negative is not going to be part of the question. The negative will be moved to the other side. So as an example, if I am asked for the antiderivative for sine x, that means somebody has already gone in and taken a derivative and gotten sine as the answer. So we're looking to see who has a derivative of sine. So right here, there's a derivative and the answer has sine. So I just need to move my negative over to the other side. It's negative cosine. And don't forget your plus c. And then the antiderivative of secant x tangent x dx. Who has a derivative of secant x times tangent x dx? Who does that derivative belong to? Well, it's right here. That is the derivative of secant x. And don't forget your plus c. We did something called the chain rule. And we're going to do just a very simple modified version of it in this section. We're going to do something a little bit more involved later on. But for right now, this is just kind of a shortcut. If you are asked for, well, we'll start with derivatives. If you were asked for the derivative of the sine, and your angle had a coefficient. So if it was like the sine of a times x, the chain rule would tell you to first take the derivative of the outside, leave the inside alone, and then multiply by the derivative of the inside, so times a. And to make this look nice, we would typically move that coefficient to the front. So we would say a times the cosine of ax. Now, because our angle is linear, because the derivative just ends up as a number, we don't really have to do the full chain rule. The a doesn't have any x's in it, and that's going to make our antiderivatives a lot easier without us having to introduce any new rules for right now. So for right now, just for this section, if we were asked for the antiderivative of any of these trig functions and our angle has a coefficient, for example, if we were asked for the antiderivative for cosine of bx, remember, derivatives and antiderivatives are opposites. Now look what we just did with the derivative. We multiplied by the derivative of the angle. We multiplied by the a. So if in the derivative we multiplied by the a, and the antiderivative is the opposite, what is the opposite operation of multiplying? It is dividing. So we are going to divide by the derivative of the angle when we do antiderivative. So first of all, there's still two things to do here. It is a composite function, so it's like we're doing the chain rule. So first we need to think about who has a derivative of cosine. Whose derivative is cosine? Well, sine's derivative is cosine. So our cosine turns into a sine, but then we also need to divide by the derivative of the angle. And instead of actually saying divide by b, I like to write it as a coefficient of 1 over b. In case there are any other coefficients, which we'll talk about in just a minute, there's a coefficient rule, we could combine it with any other coefficients. And then don't forget your plus c. And let's look at a couple of examples of this. If we wanted the antiderivative for secant squared of 4x, there's two things we need to do. Just like our normal chain rule, just like our derivative chain rule, you start with the outside. First of all, who has a derivative of secant squared? Tangent has a derivative of secant squared. You never change the angle on a trig function. The only time you're allowed to change the angle on a trig function is if you are applying a trig identity, like the double angle rule or the half angle rule or something like that. Nothing in calculus allows you to change the angle on a trig function. So don't ever change the angle on your trig function. So somebody took a derivative and ended up with secant squared of 4x. So they must have taken the derivative of tangent, because tangent's derivative is secant squared. And then we also have to take into account that they had to do the chain rule. So they would have multiplied by a 4 and ended up with no coefficient. The only way they could have multiplied by a 4 and ended up with no coefficient is if there was a 1/4 out front to start with. So all I did is I took the derivative of my angle and put it out front as a fraction. So my antiderivative is 1/4 times the tangent of 4x, and then don't forget your plus c. The antiderivative of, and this one's going to be a little bit trickier. Oop, I didn't want cosine. Cosecant 3 theta, cotangent 3 theta, d theta. This is the first time you've seen a different variable in antiderivatives. So, doesn't matter. It says do this with respect to theta. It just means the variable in this problem is theta. No problem. We can use whatever variable we want to. So this is the derivative of what? Cosecant, cotangent is the derivative of what? And if you're not sure, look back at your trig derivatives. Cosecant, cotangent is the derivative of something. And it's right here. Cosecant, cotangent, oh, it's got a negative in front of it though. That just means we need to move the negative back over to the other side. Cosecant, cotangent is the derivative of negative cosecant. So this is going to be equal to negative cosecant, exact same angle, still going to be 3 theta. But they don't have a coefficient in front here. They just have a 1 in front. And the only way they could have gotten a 1 in front, they would have had to do the chain rule with that 3 theta there. The only way they could have gotten a 1 in front is if they started off with a third, because they would have had to bring the 3 out front when they did their chain rule. And the 3 and the third would have canceled each other out. So all I did is I said, what is the derivative for 3 theta? It's 3, and I flipped it and put it out front instead of third. So negative 1/3 cosecant of 3 theta plus c. And remember, if you're not sure, you could always take the derivative and see if it gives you back what you started with. The derivative of negative 1/3 cosecant 3 theta should be cosecant 3 theta cotangent 3 theta. So that same rule with the extra coefficient inside the angle works with exponential functions as well. So one of the easiest derivatives we learned was that the derivative for e to the x is e to the x. Nothing you got to do. Nothing at all. But if it's not an x in the exponent and it's something else, then you have to do the chain rule. If all it is a coefficient up there, so if it's the derivative for e to the bx, say, well, first we would say it's an exponential, and the derivative of an exponential is always itself. But then we also have to multiply by the derivative of the exponent, which is a b. And that's the chain rule, just like with the trig functions we just did. So we're going to do the exact same thing we did with the trig functions with the exponentials. So for antiderivatives, we're going to divide by the derivative of that exponent. So if you were asked for the antiderivative of e to the x, just a regular e to the x, that's like going in this direction. For the regular e to the x, it's just e to the x. But if they want to start throwing some numbers there in the exponent, let's say e to the 9x, well, the antiderivative for an e is always going to have itself in there. The only way that they could have ended up with a 1 coefficient is if the original function had a 9th. Because whoever came in and did this derivative would have had to have done the chain rule and would have had to have multiplied by 9 in the front for their chain rule. So my 9 and my 9th canceled out to get my 1 here. So all I did is I recognized what the derivative of my 9x is, and I threw it out front as a fraction here. So we've got this special little rule, just like I had up here. So I only wrote out what it would be for cosine and sine, but you could really stick any trig functions in those spots that match up with our trig derivatives up top. The antiderivative for any e to the ax is going to be 1 over a e to the ax plus c. And we can take each of these individual types of functions and combine them to make much bigger functions with addition and subtraction and coefficients, just like we do with derivatives. And as long as they're written out term by term, we can take our antiderivatives term by term. So the antiderivative, let me write addition, subtraction, coefficients. The antiderivative for, let's say, a times f prime plus or minus b times g prime. So a is just a coefficient, b is just a coefficient, and we want to undo the derivatives on f and g. As long as they're separated with addition and subtraction, we can just do their antiderivatives separately. And coefficients just get carried along to your next step. You don't have to do anything special to your coefficients. So our antiderivative is going to be a times the original f plus or minus b times the original g. And then remember, there always could have been some constant that we didn't know about, and we want to include that in our answer. Now we can only do this term by term, and terms are always separated with addition and subtraction. If we've got x's that are being multiplied or divided, just like with our derivative, we're going to have some special rules to deal with that we will learn later. With derivatives, we learned product rule, we learned quotient rule, we learned chain rule to deal with products and quotients and composites. We will learn a special rule for antiderivatives when we see those types of things. For right now, though, if they're just separated with addition or subtraction and they have coefficients, no problem. We just do it piece by piece. So we could take the antiderivative of something like 4x to the fifth minus 9e to the x plus 12 cosine of 2x. No problem. It's got several things we need to do, but we know how to do the antiderivative of each of them. And because they're separated with addition and subtraction, we just do each of their antiderivatives individually. So my first term is just x with a power, so we can do the power rule on it. So the power rule says you're going to add 1 to your exponent. So that 5 is going to go up to a 6. And then remember, with antiderivatives, you divide by your new exponent. Now I already have a 4 in the front, and the 4 just gets carried to your answer. And then we divide by our new exponent. Now I'm going to simplify that in a minute. For right now, I'm just going to show you where everything is going. For my next term, I've got subtraction, carry your subtraction down. The antiderivative for e to the x is e to the x. Coefficient just gets carried along for the ride. Addition gets carried down. The antiderivative for cosine is sine. We're going backwards. Angle never changes. Now with derivative, I would multiply by a 2. For antiderivative, I divide by a 2, and my coefficient gets carried along for the ride. Don't ever forget your plus c. Now I do need to simplify this a little bit. So 4 over 6 can be rewritten as 2/3. And 12 halves can be rewritten as 6. So we can make these antiderivatives really, really complicated. As long as it's just addition, subtraction, coefficients, we just do them term by term by term. Now you may see a couple in this 4.9 homework where they're not written out term by term, where you do see some exponents or some division or some multiplication, but just think about your algebra. For right now, you can fix it. You can fix it and you can make it so that it is written term by term. So, for example, if you were asked to find the antiderivative of 2x minus 5 squared, now that is not written out term by term because I've got a square on the outside. That is a composite function. We've not talked yet on how to find the antiderivative of a composite function, and that doesn't mean you can't do it. For right now, that means we need to fix this. So think back to algebra. We can easily fix that. You can figure out 2x minus 5 squared. 2x minus 5 times 2x minus 5. You just have to multiply it out. So we've got to do 2x times 2x, 2x times negative 5 times 2x, negative 5 times negative 5. We just need to get this thing written out term by term. If we can get it written out term by term, then we can find the antiderivative. So 2x minus 5 squared is the same exact thing as 4x squared. Minus 10x and minus 10x is a minus 20x, and then plus 25. We've just got to get that thing multiplied out, and then we can find the antiderivative. So the power is going to go up to 3, and then you divide by your 3. Right now, this power is 1. So the power is going to go up to 2, and then you divide by 2. And then I've got a constant here. Remember our constant rule. The only thing who has a constant slope is a linear function. And then we've got an arbitrary constant. Always, every single answer has an arbitrary constant. So if you see a product, a quotient, or a composite here in 4.9, you need to use algebra to fix it because we've not learned yet how to fix those. Let me show you one more to wrap this up. If we were asked to find the antiderivative of 12x to the 4th minus 15x over 6x squared dx. Think about that for just a second. When we learn derivatives, if we saw a product, a quotient, or a composite, we had to do those derivatives with a special rule. The same thing is true with antiderivatives. So when we look at this, we see a quotient, we see a fraction. There are x's in the top and the bottom. But this one's special because there's only one term in the bottom. We can technically fix this. We can separate that numerator into pieces and simplify this. We could rewrite this as 12x to the 4th over 6x squared minus 15x over 6x squared. Both of those terms want to be divided by 6x squared. And because there's only one term in the denominator, it's going to be really easy to go ahead and simplify this. So this is the same as 2x squared minus, well, that one doesn't simplify to a whole number, but they at least have a 3 in common. That's 5 halves. X to the negative 1. Or you could write it as 1 over x. It's up to you. So we can fix that one as well. And it's because there's only one term in the denominator. That's the key. So now we're ready to take the antiderivative. Antiderivative says you're going to add 1 to your power and divide by your new power. I'll bring my subtraction down. Remember, we can't do power rule on x to the negative 1 because it's going to make us divide by 0. What was that rule for x to the negative 1? That was our special case. What does the antiderivative of x to the negative 1 turn into? Remember, it's 1 over x. Who has an antiderivative of 1 over x? That's our one special case that you need to remember. That's natural log of x. There's our antiderivative. Okay, so watch out for any that you see that have multiplication or division or any weird composition like with squares on the outside, because you're going to want to fix those with algebra. As long as they're written out term by term, you can go ahead and fix them and find the antiderivatives. And if you have any questions whatsoever, just email me and I will be happy to explain any problems in more detail.